Good morning. Welcome to my short presentation on printed microheater on textile thread for moisture measurements. I am myself Manoj. I'm working as a scientist at Silicon Austria Labs. I will start just by introducing our research institute, Silicon Austria Labs. It's one of the Austria's leading research institute for electronics and software-based systems. We are performing cooperative and application-oriented research along the EBS value chain. Silicon Austria Labs is in 3 locations within Austria, and it is in Graz, Linz, and in Villach. I am basically located in Villach, and Villach is one of the beautiful town in Austria, southern part of Austria, and our research group focuses on sensors, basically sensor systems, and within that group, we are more focused on printed flexible electronic sensors. So today I am presenting a short work, a feasibility study of one of our work, and it is about moisture measurements in textiles. When we talk about moisture measurements in textiles, why we have to do this? There are different reasons for that, like, for example, different use cases for health monitoring applications, but it is not limited to that. It is also like, industrial filter and other applications are also there. However, today we are a bit more focused on wearables. So these are the different reasons why we need to measure the moisture. How can we measure moisture in textiles? The most common way to do this that we see in literature, that is basically electrical measurements like capacitive or impedance measurements to know the moisture content. It is usually a simple measurement. However, one of the problems that we see there, especially when it comes to the body fluids are very heterogeneous in nature with ionic and other components are there. So this varies from time to time and person to person. So this is always an issue. With electrical measurements, there are always errors. For example, set rate, this is usually we see a lot in the literature that set rate measurements are always causing a lot of problems due to this error measurements from the ionic concentrations. In a literature, there are studies which shows thermal measurements can overcome this problem of this ionic variations doesn't change the measurements much. So this is one of the way to overcome this problem. So we are going to talk about that part, this thermal sensing, and first we see how this is going to be done. This is a transient thermal measurement, means it is only for a short period measurement. A short period, we do this thermal measurement, a heating pulse. And here the sensor is basically works on the principle of on the basis of the material property called thermal effusivity. Thermal effusivity is something like the ability of the material to exchange heat to its surroundings. For example, when I touch this wooden thing, I feel it's a bit warm, but when I touch something metallic, it feels a little bit more colder. So this is basically because of this material property called thermal effusivity. And thermal effusivity of water is much, much higher than air or like textiles, dry textile, for example. Here we have a thin film heater, a PTC, a positive temperature coefficient heater as the sensor. And we trigger a heating pulse for a short period, like maybe 1 second or below a few hundred milliseconds. And there will be a rise in temperature, that is delta T. This delta T of this heater or the sensor is a function of thermal effusivity and time. In the case when we have a defined power and time, it's basically depending on the thermal effusivity. So here I have a graph shows like the rise in temperature of the heater in 2 different situations. One is when the sensor is dry, means it's basically air. In that case, or dry air or dry textile or air, in that case, the temperature buildup will be more steep compared to the one when there is a wetness. Due to the when there is a wetness means liquid or like water content, this has higher thermal effectivity that leads to less temperature buildup. So from there, we can see this, moisture content and how this is related to the thermal efficiency. This change in this difference in the heat buildup, this can be also be measured using the resistance measurement. Like basically, this is the formula where the delta T, the rise in temperature, is related to the resistance at any time point. So this is the sensor principle, and there are different approaches to do. Already there are in literature there are multiple ways we have developed the sensor. One is simple microfabrication, just on a foil with coating and etching or photolithography and etching. A gold structure is patterned as a heater, and then this foil sensor is being attached on the textile, and that has been used for measurements. And another way is to directly print textile, this heater structure on the textile substrate. Mostly it is used to screen printing, and like silver or carbon, these are the material we can use for such measurements. So at this point, the question, so there is already a sensor. If you go to this literature, you will see some measurements, nice measurements where this thermal principle, transient thermal measurements used for moisture measurements. So we need to go beyond this situation, or like there are also like, if you have a foil sensor on textiles or directly printing big structures on textile, this is maybe not always the best case. It is not always very user-friendly or convenient for people to use, because no one wanted to lose their textile texture and its imperceptibility, and all these factors are very important here. Additionally, sustainability is another part that comes in. So we have recently published to something that can be a solution to effective, more effective than this current existing methods. That is, what we do is we directly print sensors on thread or fibers. We can directly pattern sensors. So the advantage is here, it's imperceptible. And multiple sensors can be on a single thread so that it can be used anywhere. Like maybe in one use case, it may be a wound monitoring. Another use case, it can be for sportswear. So this is the thing I want to go a bit beyond now here. What we do is we are printing directly on thread. And here we mostly used two different types of process. One is non-impact process, like aerosol jet printing. And that gives very intricate structures very precisely. We can go down to 40 micron line widths. And the other process is screen printing, which is impact process. However, here, since it is on textiles, it is rough. And the most common process is, of course, screen printing. We used it because it is giving more thicker deposition, and surface properties are relatively less detrimental compared to aerosol jet printing. This is the process where we have a the thread is placed in a sample holder or a printing bed where there we have a channel, and then we have the normal screen printing process. Once the alignment is done, then this is a normal printing process, and we can have mostly any structures. These are some of the example cases we are showing, like to show how this would look like. There are carbon, silver, different materials can be printed. However, here in this work, we have used carbon and silver. So I come back to the micro heater part on thread. It is basically a simple heater made of carbon element, printed carbon, and it is having also the interconnections lines with the silver. And also having a coating which covers the protection to make the protection. After the fabrication, we tested the heaters just with thermal imaging systems to check the heating uniformity, where you can see this reddish part, which is the carbon element comes. And also you can see this rise in temperature and the stability of the heater on the next image. This greenish part, what you see is the heat progression over this silver interconnects from the heating part of the carbon, that is just thermal conductivity. The moisture measurements, we did it just by putting this sensor, this thread, and then we have a textile substrate on top of it. And we have a heating pulse by applying electric voltage. Then we drop a drop of water onto the textiles. The measurements we did, basically we just need to check, we make a heating pulse for a second, and that time we see this resistance change. That's what we see on the first image. And the second one, you can also measure the change in current as well. It's basically same current or the resistance or the current. So what I'm showing here is just the primary results of the moisture sensing. Here from the measurements started once the droplet is on the textiles. From there it is started and it went for a few tens of minutes. So at certain intervals, we measure the heating, we check the heating pulse and measure the resistance or the change in current. What we see is that the textile drying over time has been very well seen over a period of time. And so wet to dry transition was very clearly visible there. And this change can be also, if we just measure the slope of these curves, this can be directly correlated to the moisture content within the textile. So this is the outlook. Mostly it's in the, it's a feasibility study, and this would lead to more imperceptible with the maintained textile properties for more accurate body fluid measurements. And thank you.